All right, I think we're above 50, so let's get started. So welcome back, everyone, for Adam Martin's lecture number 2 on effective field theories, or baby newts, and the standard model effective field theory.
All right, good afternoon, everybody. Or, I don't believe it's morning for anybody. Hope you're doing well. It's been another couple of busy days, I see, for you. As we're talking about, going to dive right back in. And as before, let me remind myself to, chat questions up, so please feel free to interrupt me. Our plan is, unfortunately, or fortunately, depending on what you like, today is going to be a sort of the most technical of the lectures that we're going through, which terrifies me, but probably as much as you. Because we're going to have to do some loopy things. And I mean, because we are doing quantum field theory, and a big reason or motivation for doing EFTs is why they're behaving better once you start to include quantum protection or corrections. Not why they are, but the fact that they are, and to see that, borne out. So today we're going to sort of finish at an unfortunate spot last time, in the middle discussing some redundancies. We just sort of recap that briefly because it was the end of the lecture. Started talking fast. I say things not as correctly or as clearly as I would have liked. Then we're going to talk about loops and RGEs for EFTs. And this will bring in, we're not going to do, I promise you, I'm not going to make you combine denominators, do the loops, but we're going to need to have, bring back from the back of our brains some, basic stuff about loops. And yes, if you continue to Wikipedia or Google EFTs after baby newts, you will find emotional freedom techniques. Definitely an alternative measurement. I like the fact that it involves thought fields. So EFT in terms of effective field theory is way down in the Google list. We've got to do some work to get ourselves back up there. So again, if you've learned nothing else, do the other things that EFTs stand for. So we're not going to do thought fields. We're going to go back to our QFT. And we're doing, at least for the lecture and this one, sort of the top-down perspective. I've got a UV full theory, and I want to think about a replacement infrared theory with fewer degrees of freedom that's doing the same thing. We sort of learn by example. And here was the full theory that we had. Right, we've got our light field, which is this fermion, heavy field with that scalar, and the EFT that we replaced it with was this one right here. And as we talked about, this goes on, but at least the leading terms in terms of power counting, buzzword from last time, were a 4 fermion operator. So I'm sort of, yes, these are higher dimensional terms. I'm absorbing the dimensions into these guys. So we had a 4 fermion term and a 4 fermion term with derivatives. We marched through how you match them. We said we match them at the scale of the mass of the heavy particle. And we got a value for that coefficient C and D. Right? That was one of our accomplishments. What we want to do now, just remember that example. We're going to continue to run with it. Before, what I ended with last time was just a redundancy. One of the main messages that I wanted to get, forget any of the details, factors of 2, I definitely forget that stuff. One of the main messages I want to drive across is that a higher dimensional Lagrangian term, an operator there, you can always mess around with it. So you should never be too attached to a higher dimensional term. And the way I sort of addressed it was there's a redundancy that if I just take phi to phi plus delta phi, it doesn't change on-shell amplitudes, the stuff that I connect to experiment. So the example I had was, here's a theory. We've got usual dimension 4 piece. We've got some dimension 6 term that's got d squared in it. And we know d squared, part of the equation's motion. And then we've got, sure, there could be other dimension 6 pieces and beyond. And what I said, and feel free to do this, I think it's an insightful exercise. You just plug in phi to phi plus c phi cubed over lambda squared. You get this Lagrangian LB. And of course, these are plus dot, 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 and plus dot, dot, dot. These look different. Right? This has a quartic term. Right? This doesn't. But you go ahead and you plug in and you calculate phi phi to phi phi, the actual amplitude. You have to be a little tricky. There's combinatorics that come in, or phi 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 to phi phi phi. again, physical amplitude, you will find they are exactly the same in both of those theories. Now, one of the things that came up was, you said, what is the, or I even said, let's just write it down. So the net result is whenever I have a higher dimensional operator with d squared phi, I can replace that with minus m squared phi. We can, which effectively looks like we're just using the equations of motion. And yes, that's what it looks like, but the truth or the reason behind it is this field redefinition coming from this redundancy here. That redundancy allows us to do transformations like this, which result in just using the field equation or the equations of motion. Not specific to scalars. Similarly, if I'm wandering around and I see a higher dimensional term that looks like id slash phi, I can just write that as, m times the fermion, similar for gauge fields. Right. So net result is just that, but it does have its origin in a field redefinition. Why do I make this big point? Well, if we say we can always do this, why don't I just look at the Dirac Lagrangian and say, well, that's 0 by the equations of motion, because d slash equals the m, I just replace it this way and it makes the whole Lagrangian vanish. Well, we can't because there's no field redefinition that would actually make that happen. So this stuff is happening in, excuse me, it's all happening in higher dimensional terms. Not the dimension 4 or less Lagrangian. And another thing that I sort of didn't specify completely clearly last time is you're always just using the dimension 4 or less equation of motion. So you can imagine I write down a theory and it's got, L and it's got some dimension 4 Lagrangian plus, oops, some thing at dimension 6, IQ. I can remove, or I can swap this out for minus m squared using the equations of motion, or using this field redefinition. See, even I'm guilty of this. This will give me something that's minus m squared, c phi to the 4th, lambda squared, plus. There are always going to be higher order terms. And it could be that later on, or at higher dimension, there's a term that looks like, say, d phi to the 5th, d squared phi over lambda to the 4th. Well, now that I've removed all of the stuff at 1 over lambda squared by field redefinition, I can do another field redefinition to remove the stuff at 1 over lambda to the 4th. And I can just keep doing this if I want. And the thing that you're using is always the free equation of motion. I said this in sort of a confused way last time, which is why I wanted to clarify it. And again, even I'm guilty of it. I keep saying you use the free equation of motion. That is the net result, but really the physics behind it is this field redefinition. So we've got this redundancy, and it doesn't have to go this way, always derivatives to mass. Say I like derivatives. You can go the other way too. I can take a mass term and turn it by the equation of motion, same thing, the same field redefinition, really, into a term with derivatives. So I should never be particularly attached to this term as an operator in the Lagrangian, or to this term as an operator in the Lagrangian. The things we care about are those guys, because that's what's left the same. And you say, this seems kind of overkill, and it is here, but this is something that people tend to forget and just ignore when it comes to a more complicated effective field theory with tons of fields and more complicated equations of motion, like the standard model effective field theory. So we've got this redundancy, we've got integration by parts redundancy. Don't get attached to a particular higher dimensional term in the Lagrangian. Get attached to their effects and observables. All right. That's what I wanted to say to sort of clarify that. We're now going to move on to, let's talk about some loops. So just as our backdrop of our problem, here's our little graph of energy again. We've got this scale m. And we also could have a scale way down here, mass of the fermion. We matched our two theories right up there. But now I want to look at processes at, way down here. our Lagrangian that we wrote as a toy theory was a little sparse. So what I want to do is actually put in a few more interactions to make it look a little bit more interesting, and that will sort of frame the problem that we want to look at. So instead of that toy theory that I wrote last time, the toy theory we're going to do now is the same as we had before. We're just going to add a gauge field. We're basically going to make that fermion charged under an electromagnetism thing. So we're going to have our full theory is now psi bar I d slash phi minus m psi bar psi. And of course, we've got, so basically think one fermion charged under QED plus a heavy scalar. All right, here's our heavy scalar. One fermion, QED plus a heavy scalar. So then more specifically, oh, and we can specify, you know, this guy is, as usual, the process that I want to look at and where we're going to see the loops coming in a way that doesn't involve us having to do tons and tons of work is I want to look at psi psi to psi psi, same process as before, but now at order, you know, kappa squared. So one exchange of that heavy particle plus some loops of the photon, right? There's a photon here now. All right, so we've made our full theory a little bit fancier, basically because I want to talk about loops of something, and it's easier and involves having to take us through fewer steps if I don't just do loops of this kappa coupling, but if I do loops of kappa plus an additional coupling. So if we're in the full theory again, that means the kind of process that I'm going to have is, all right, there's my scalar exchange, but I'm also going to have a photon. I'm just going to call this guy a photon the whole time. Right? And the reason this is a nice, easy theory to work with is we know a lot of things about QED. So I'm just going to rip stuff from QED when I need it and put it in here. All right, so here's our one possible diagram of this kind of scattering at this order in couplings. And we're still working at an energy S equals mass of the light field. Okay, there's a lot more diagrams. Here's just one more. If I want to do this calculation of full theory, I have to do all of those, right? So my loops involve the heavy particle by my light fermion and this massless gauge. I'm restoring the mass of my fermion. I had shut it off. You guys were playing minute attention in the last lecture because I didn't want to deal with it. Now I want to put it in so I don't have any infrared nastiness. Right? So I'm not going to do these loops. The whole purpose of this lecture is that they're hard to do. But if I was to do this, we would schematically get something that this at one loop, well, that's going to equal the, at tree level, times 1 plus, all right, there's going to be some constant. Remember the tree level piece, this has got the k squared, kappa squared in it. So the thing that's going to appear in the correction 1 plus is just this gauge coupling here. And I could have some nasty logs that appear, like the ratio of this super or this heavy scale to this light scale. You say, all right, what's the big deal? I can go ahead and calculate that. People are super experts at calculating. The problem is that this thing doesn't have to be that small. Right? I'm in my imaginary universe. I can do whatever I want. I can imagine that this hierarchy of m over little m is huge, huge enough so that maybe this thing is not order 1, but it's order big enough that if I want an accurate prediction, I should go beyond first order. It means I would have to go to 2 loops or 3 loops or whatever. And that's a pain. We would like to avoid having to do so many extra loops to get an accurate computation. And that's the thing that working in the EFT allows you to do. By working in the EFT framework, you don't have to do as much, you know, loopy math, and you still get you can get a more accurate setup. So this looks hard. What I want to do instead is let's do it in the effective field theory. Effective field theory doesn't have the particle capital phi, right? It still has our fermion, which is charged. So it still has that kind of vertex, still has that kind of vertex. And we know that this could either be a 4 fermion C, or it could have derivatives. That guy had D's with it. So if we're viewing this in the EFT context, the problem here is that we know that we matched, we found these coefficients, right? Everybody recall what C and D are, right? There are these coefficients here. Right? We matched them, so we knew their value at tree level. So we can say that they had some value at a scale M, and we'll also have D, and we want to know their value at a lower scale. So viewed in the EFT, if I want to know this process, we need essentially C mu equals this low scale. Right? We know the operator, or we know the coefficient at the high scale where we match the theories. I want to now totally forget that the full theory exists. I just view this problem as a renormalization group problem. I have this coupling at one scale. I need it at another scale. So what we're going to do for the next, it's going to take a little while, is figure out and calculate how to do an EFT for, this is a, composite. That's a 4 fermion operator. We want to know, how do I get the RG for it? How do I avoid some of the traps that you might think when I naively say, here's a dimension 6 operator, let's renormalize it. This is what we want to do. Now we know C, remember this is psi bar psi squared. Technically, yes, we had this 4 fermion operator and 4 fermion plus 2 derivatives. What I want to do is just forget that that guy exists. So let's focus on C. Remember, that was the coefficient of psi bar psi squared. And you could feel okay about doing that. Remember, D was technically a dimension 8 operator and therefore came in at a higher power counting than this C, the C coefficient. So, okay, we can focus on this without feeling like we're, neglecting something terrible. So we often do, we know how to do RGs for renormalizable couplings. We do this, we do beta functions of QED, QCD in our QFT classes. We've probably done it in our research. What is less done that often, and why I want to focus on this here, is how we do it for a higher dimensional operator. Right? Higher dimensional operators have the label non-renormalizable. So we're going to do the oxymoron of renormalize the non-renormalizable thing. So it's like military intelligence, except that this one you can actually do and works. We can renormalize this. The stigma of non-normalizable, we'll address that, isn't going to play a role. So we can just ask issues. No. Just treat C like any other coupling. So when we're doing EFTs, we tend to have this, or at least I tend to have this doubt, or not a doubt, it's really this bad labeling where I'm always viewing the EFT as sort of this leftovers of a more fundamental theory. Say, yeah, okay, really it was the standard model, but at these energies, it's just these few particles. And that gets us into trouble. The right way to think about this is an EFT is a totally fine quantum field theory all by itself. It does not need reference to that other theory. Right? We matched the two, and that was certainly a boundary condition in our EFT, but it doesn't need that guy to have its validity. It can have its own renormalization, as we're going to see. It can exist, it can be predictive. We can do all sorts of things with it. Just treat it as its own quantum field theory. It has its own hopes, dreams, etc. Doesn't need that other theory, right? That other theory there only provided this boundary condition. So why this, spiel about how great this theory is by itself? What would we do if I just said, here's a theory, find how that coupling runs? Well, there's a couple of different ways to do this. I would do this as we were just going to do renormalized perturbation theory. All right, renormalized perturbation theory. Sir, you say, let's rewrite our Lagrangian. We're going to do it in terms of things that are connected to measurement. So physical fields, physical couplings. And the usual steps that we do is we say our Lagrangian I can write as, in terms of these things called bare fields, bare couplings. Right, again, remember, I'm just going to neglect that coupling D for a second. And we say I can rewrite this, and I could certainly do calculations in terms of these bare parameters here, but that's a pain because those guys aren't measurable. Fine. So if I want to rewrite this in terms of renormalized, measurable things, this is when our little Z factors come in. So these guys are the renormalized fields. This is the renormalized mass, pole or thing that you could go and measure. This is the renormalized coupling. That's connected to experiment, meaning that I would go and measure psi-psi scattering at some certain reference scale, and I would disentangle some of the momentum stuff and equate that measurement with this value. So this is a physical quantity. Right? The price that we pay for working in terms of physical things is we've got these Z's here, which we then usually separate out into vertices plus counterterms. Counterterms are just an annoyance that we have to deal with for the luxury of working with these physical things. So we've got our I psi d slash psi minus m r psi bar psi. Right, renormalized perturbation theory. Right this way, we've got these counter terms. They're an annoying nuisance that we have to deal with. They're there to make sure that we get nice finite things. They are often infinite, or they're often really depend on how we're regulating things. They never appear in final answers, or the final answer, let me back up here. So we've got our counter terms. And we've got our, physical quantities, masses, fields, etc. So we have this nuisance. If we want to do a normalized perturbation theory, we've got those nice fields, but we have to drag around our counter terms, which are there to make sure that we get finite things at the end. Not only this, but when we do renormalized perturbation theory, Lagrangian alone does not specify things. We also specify we have to have a renormalization condition. Right? The whole idea of renormalization is I'm writing observables at one scale in terms of observables at some reference scale. So all of these quantities are physical quantities here. They drag around some dependence on that reference scale. We're all familiar with this. It's the same thing happening here. The fact that C is a coefficient of a higher dimensional operator hasn't come in yet. So then we're going to get renormalization group equations are the fact that I could do calculations this way with that bare coupling, which wasn't physical but had no dependence on things like reference scales, or I could do it this way. And since they're both equal and this way has no dependence on that reference scale, we can set up an equation here. Mu is some reference scale. This guy doesn't depend on any reference scale, and that's what we're going to use to solve RGs. Same thing that we've done for beta function or for QCD, QED. It all looks the same so far. The fact that C is a coefficient of a higher dimensional operator has not played a role at all. And we're going to stick with that, and we're going to see that that continues to hold. Right? As an intermediate step in calculating all this, we have loops which are infinite. We know we have to regularize them. Right? That's where we put in our cutoff, put on our polyvolars field, putting whatever we want. But at the end, we know that the regulator has to disappear. Nothing physical will depend on the regulator. This is something that we learn, we go, yeah, 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 and then we tend to forget and assign more physical meaning to intermediate steps that involve regulators than they're actually deserved. So we know at the end, yes, there's a regulator involved, but nothing physical depends on it. This is important to remember. All right. So now we go on our way. If I want to figure out how this coupling C runs, I need to know something about those counter terms. Specifically, I need to know this guy, the field redefinition that's going on for our fermions. Okay, let's see, we can start drawing some loops. I'm going to have a term that looks like this. We know that our fermion's charged. I can just close a loop, no problem. But we could also have diagrams where I take that C vertex and I just close the loop like this. Right, so hiding here is C. Well, we know how this one scales. We've done this. This is just in your favorite field theory textbook. Let's try and do some estimate for the size of this diagram. Well, we know it's a field strength renormalization, so it better be proportional to P slash. It's got an insertion of that coupling C. And then there's going to be some loop momentum or some loop integral. Right? The K squareds are coming because I need a P slash here. Right? If you do this, the simplest way that we can say how to do this is we just say, all right, loop, we say only continue momentum up to some scale, especially if we're considering the EFT as some leftovers of a bigger theory. We say, okay, this guy has to have some cutoff at his scale. We would say that this is then P slash C, some lambda cutoff squared, right? I do lambda with a C because this is different. I've used lambda, capital lambda before as the scale suppressing our higher dimensional operators. I don't want to get anybody confused. This is just some momentum cutoff, right? If we put in what C was from the matching, we would find that this is K squared C over M squared. I could do the same thing, putting that D diagram in. Right? The dimension 8 operator with derivatives, right? D mu phi, D mu phi. You would find the same sort of schematic calculation gives you P slash K squared M to the fourth C over M to the fourth. So a natural value you would think when you're doing EFT is to put that cutoff where I'm limiting my momentum to be M. That's a huge problem, right? Because it says this diagram is the same size as this diagram, is the same size as this diagram. So yes, we know that this regulator stuff is only an intermediate step, but if we use a hard cutoff, all of a sudden we've mixed up all of the terms in our power counting. The only reason that we argued we could get away with having infinite interactions in an EFT is because we said at any finite order in the power counting, there's only a certain number of interactions. This is messing that up because now this term, which is naive, or when we looked at tree level, higher order in the power counting than the one without derivatives, now they're contributing the same. So this makes us say, oh my goodness, we're really screwing something up here. Loops and EFTs are going to be hard. But all is not lost. We just have to think a little bit harder about what is a loop. What does that mean? So what's in a loop? And like I said, my brain works entirely on examples. So if you want to carry an example around, let's use that one. This is a loop diagram. Right? Forget physics for a minute. Right? This is just a complex integral. Yes, we would rotate, we would do this with poles. Right? And all one loop diagrams, that's what they've got. They're just complex in K space with poles. You go beyond one loop, it's a little bit more complicated, but not severely. Don't ask me any questions about beyond one loop. I've try to avoid it. So this is just a complex integral with poles. And we can draw it. Where's our poles? All right, after we rotate, we know our poles are sitting right up here and down here. And here's our imaginary K plane. Let's think about what physics comes out of this. Yes, sure, at first we said, yeah, really it's just a complex integral, but we're here to do physics. So let's think about ranges of momentum. If K is around equal to M, well, I can't expand any of those. Neither K nor M is particularly large. So I can't expand that. I've got to deal with that whole denominator. This is what I would call the pole region. This is where we're dealing with physics, you know, in that area. This is the important stuff. What do I mean by this? This is the regions of momentum that will give rise to log m squared, or really log p squared, where p is the momentum of some loop, of the external momentum going in some loop. That stuff is super important. Why is that super important? Loops are related to trees, cutting these things and finding the imaginary parts in them. That's the optical theorem. The whole reason that loops have to exist is because of that optical theorem in some way. So the imaginary parts that are telling us unitarity, optical theorem, those are coming from logs. Right? That's the only way you're going to get an imaginary part. So the important physics in this is coming from this pole region. Right? That's not super high momentum. That's momentum around here. If I go to this super high momentum, K is much larger than M. I can expand that denominator. This is going to be 1 over K squared, 1 plus M squared to the K to the 4th, or K squared. No poles, right? I'm thinking way out here now. This is all analytic in any of the external parameters. In masses and external momentum. This is exactly the stuff that we shuffle around with renormalization. The very high momentum, the divergent stuff over here, is what we shove into our constants, into our bare constants, in order to renormalize the theory. So this is all the stuff that gets shuffled away with renormalization. Exactly how it's shuffled depends on the regulator, but as I emphasized before, regulator never matters. So the physics out here is always shuffled away. This stuff does not matter. Getting a little too creative with colors here, pardon me. This is all shuffled away by renormalization. We're absorbing it into our field redefinitions, our coupling redefinitions. We're absorbing any of this junk. It depends on the regulator, and therefore it's not physical. So if the stuff that I really care about is momentum in here, and I don't care about momentum in here, or I know it can never have a physical impact, why don't we regularize, why don't we attack these integrals in a way where this stuff causes as little distraction as possible? The way I know how to do that, and the way physicists do this, is we deform this integrand so that I can do this contour integral and close the contour at infinity. Right? I deform it so that it is no longer divergent way out here. When I do this contour integral, we know all of the physics is then picked up just from that pole, its location and its residue. As I argued here, that's where the physics is. That's where the stuff that can stick around. Sure, you might be tempted to say, oh, this stuff's super important. It looks super important when you do a cutoff, but we know renormalization will shuffle away all cutoff effects. So the way to do these integrals with the least distraction from any of this junk, that's why we use dim reg. Dim reg is whatever I just said. You deforming the integrand so I can do that contour and just pick up the physics of those poles. So we're gonna do a little dim reg here. Dim reg for me is d equals 4 minus 2 epsilon dimensions. I am sorry for this, or I don't know if I'm sorry or if other people are sorry. This is super common, well done convention. Unfortunately, this is not the convention that Peskin or, oh, I'm not gonna spell that right. They do not use this convention. They do 4 minus epsilon just to drive anybody crazy who's trying to write EFT lectures and wants to compare it to something. Sorry, So this is much more common by people actually doing loops. Many of the formulas are going to look very similar, just going to be some factors of 2 hanging around. So we're going to do a little bit of dim reg. We've argued that that's still getting us the physics I care about, and none of this stuff is going to matter, or it's going to be minimally impactful. Okay. Now applied to an EFT, this answers a question that lingers in everybody's mind. If I'm doing an EFT, the problem with dim reg, let's write down dim reg. And I've got some stuff. This naively looks like you're integrating over all momentum, right? There isn't a cutoff that says only go up to some scale. You says integrate over everybody. So here's a nice little loop that we might have in an EFT. You might worry, aren't I accessing momentum that are invalid to the EFT because they're beyond wherever I declared this guy valid? And the answer is, it looks like that, but remember, in dim reg, all physics coming from these loops is coming from the poles, right? I have messed with the integrand so I can do this. As long as I add no new poles, I'm totally fine. So we can work in an EFT. EFT has these poles from our light field propagators. I can do the whole integral, capture those poles, and I never have to worry that I'm screwing up. Can I do 4 plus 2 epsilon dimension? If you want something, so the reason we do 4 minus 2 epsilon dimension is it makes things more better behaved in the UV. If you're worried about the opposite problem where you're dealing with IR divergencies, that's when you want to go to 4 plus 2 epsilon dimension. But these guys are defined and sort of be analytically continued into each other. So yeah, you certainly can, and people do when they're worried about infrared physics problems. So the little end of this little what's in a loop discussion is, let's do dim reg. Dim reg is picking out the physics that I care about, poles, little distraction from the physics that I know is not going to matter in the end when I'm actually doing a meaningful calculation. Does this actually solve our problem? Key thing about dim reg is there are no new scales. Right? When I do this integral, I didn't introduce a capital lambda. The only scale in the problem is m. And that is super important. So let's look at this calculation again, right? Reminder, this was that vertex C for fermion, and I'm worried about how that would cause some impact into my field strength renormalization. We said this guy was p slash k squared over m squared, and now we'll do our little dim reg. We're not going to go through how to do this integral. We know just by dimensional analysis, right? This quantity, that better be dimensionless, right? We have a scale capital M there. There is no new scale introduced by dim reg. The only scale around is this infrared scale. So this has to go like that. Shouldn't the k squared be inside the integral? This is where I have made a poor choice in couplings. This k is actually a kappa. That was the Yukawa coupling that I was using, right? Way back in the beginning. This is a, yeah, sorry. That is just a poor choice of notation. All right. So this then preserves power counting. Because these diagrams is much, much less than this guy, which has no little m over capital M showing up. Right? So if we do dim reg, this power counting, which made us breathe a sigh of relief and say we don't have to include infinite terms, that is preserved, providing you're using dim reg. So I have a collaborator who says, do a calculation in whatever scheme you are, in whatever regulator you want, as long as it's dim reg. So that is my philosophy, dim reg. Right. Dim reg is a little bit annoying with gamma 5, but we're not going to have that issue here. All right. So hopefully I've convinced you, if we're doing EFTs, dim reg is the way to go. right? It doesn't, it gets us away from this weird issue that aren't we including physics that we shouldn't be? No, it keeps the stuff that we care about, and it keeps our power counting. Power counting is crucial because that allows us to not be exposed to having infinite terms. So let's talk a little bit of housekeeping about dim-reg. If you have just changed the dimension of space-time, you will change the dimension or the scaling dimension of fields. So now fermions scale as 3/2 minus epsilon. Gauge fields and scalars now is 1 minus epsilon. Okay? Just a fact of life. So now if I look at some action, well, it's going to have d4 minus 2 epsilon x. It might have some term like psi bar, gamma mu, psi, a mu, and here's our good old electromagnetic coupling. If you go ahead and you plug in dimensions here, we know how those guys scale. We know how these guys scales. You would find that the scaling dimension of E is plus epsilon, right? That becomes a dimension full constant, right? Makes sense. We have marginal couplings, 4 dimensions only, right? We've screwed with that. We're not in 4 dimensions, so we've screwed with this. That's kind of annoying. So a way to get around this is we usually compensate, and I will rewrite this term as E mu to the epsilon, psi bar, gamma mu, psi, a mu. So now this guy holds our dimension. E is still dimensionless, right? So if you're ever looking at a paper and you see them walking around with couplings that look like this, with weird factors of mu, hint that we're all in dim-reg. This mu, this is the renormalization scale. Remember, renormalization, we always have a reference scale where we define our parameters at, and we're going to rewrite things in terms of them. This is that reference parameter. Physics can't depend on that reference parameter, so we're going to use some invariance into that for our RGEs. This guy only, crucially, only appears in logs. All right, and similarly, we had C psi bar psi squared. This is going to become C mu to the 2 epsilon psi bar psi squared. All right. All right, let me talk for a few more. Should we do the same for whistle group? Yes, absolutely. That's just what I did right there. All right, so this preserves the fact that C is dimensions of 1 over mass squared. Yeah, absolutely. So in dim-reg, the RGE comes from is basically that this bare coupling, which we could have calculated things in terms of, doesn't depend on this reference scale. But when we've written things in the renormalized perturbation theory, they do. So this guy is equal to mu, mu to the 2 epsilon. We've got that renormalization parameter z there, and z renormalized. And this has all got to be equal to 0. Same thing that we do, beta function, the fact that this was a higher dimensional operator, no role. Because we're able to separate this and only we deal with things and not bring in terms from higher power counting. All right, we just expand this out. This is going to tell us this is our goal. How does the coupling run with mu? Right? We are used to calculating. We're used to something like mu d g strong d mu, mu d e d mu. We've calculated those. We're doing the same sort of thing, but here. So if I want to solve this equation, I need, this is what I want, I need to have some of these ingredients. is sort of step one. We can look at tree level. There, these guys are equal to 1. Right? The counter terms are there for infinite things coming from loops. We don't have any loops. Right? So if I do that, that tells me that mu dCr d mu minus 2 epsilon CR. Whoops. Right. I've deformed from 4 dimensions. This is just telling me that the operator that CR multiplies now has a weird scaling dimension because I have an epsilon. So this is just telling me that if I go change the dimensions of space-time, operator dimensions change too. I'm used to calculating ZG and ZE, but I guess it's equivalent up to a 2 epsilon and sine because of that equation. Yes, right, we're gonna see, of course, right, in the end, we always take epsilon equal to 0. So things like this are going to vanish once I have when I go beyond tree level. So yeah, I think the answer to your question is yes. In fact, if I was to do 1 over E mu dE d mu, just how the electromagnetic coupling runs at tree level, but in 4 minus 2 epsilon dimensions, I'd find it's minus epsilon E. Right? We're used to calculating the order E cubed part here. Right? Once I go to 4 dimensions and I zero this guy out, all I have is the part that we're used to. We're saying that if I'm at tree level, or if in 4 minus epsilon 2 epsilon dimensions, even at tree level, those couplings have some behavior with mu, which makes sense. I'm no longer in a 4-dimensional theory where I have marginal couplings. All right, now we have to go about this. We need to calculate Z. We need to calculate things like this. We're going to do this quickly. And when we do this, so we want mu dependence. Right? That's what's sticking in here and sticking in here. But we have a trick. In dim reg, mu dependence is always married to 1 over epsilon. So we always see this. That combination always appears together. So if I want this dependence, I can just focus on getting that dependence. They appear with the same number in front. This makes life easy because if I want just the 1 over epsilon piece, right, that's the most divergent piece when we're doing dim reg. If I want the most divergent piece, I can simplify life by saying kill masses, kill external momentum. All that stuff is usually lowering the degree of divergence. So this says, doing it this way, we're sticking in dim reg. All I'm going to do is write down some integrals where I want to pick out the 1 over epsilon piece, because that is a proxy for the mu piece. So I guess step 2 is the fermion field strength renormalization. That's this guy, plus now we've got our counter term in there, and we're going to adjust our counter term so that this is finite. All right, if we go ahead and do a loop, I'm not going to do the loop out for you. We could combine denominators. You would use some general dim reg formulas that I put in the supplemental material. This guy is and this is IP slash. So I want to solve that so that this is finite. There are lots of ways that we're going to do this, and how we do this, exactly what finite pieces I shove in there is somewhat up to me. I'm going to use the minimal subtraction scheme, where I just put the 1 over epsilon piece. This can affect intermediate steps, but as long as we're being consistent, there's going to be no issue. All right. So then this is an easy equation to solve. I want to adjust Z such that I absorb the 1 over epsilon piece into it. That tells me Z psi is 1 minus E squared 16 pi squared 1 over epsilon. Cool. First ingredient. Actually, it is 4:52, at least for me. Let's take a 2-minute break. Feel free to fire some questions at me. We are, most of the way through this derivation. So let's take 2 minutes. Is something wrong? Is something wrong? Don't factor out mu Wilson coefficient. Does our choice? Is something wrong? Don't to factor out mu to the 2 epsilon from a Wilson coefficient. Does our change of running? I don't quite understand that question. The mu factors out front. You're absolutely correct. Whoa, erase the diagram. When I'm doing this, these vertices here are E mu to the epsilon. They come in there. I think d log mu. Ah, you're right. Yes, sorry. Absolutely correct. E's on too many sides of things. Hope maybe that clarifies the previous question. All right. Coffee, required sustenance when doing loops. Okay. Let's push through. We are almost there. Could you explain the power counting preserving statement from the above diagrams? Sure. Absolutely. Let's go back to, that goes back to this. Right? We're trying to organize things in terms of, here's a set of stuff that has no powers of p over lambda, and p here is mass of our light particle. Stuff that has one particle power, well, that doesn't really appear, so we have no powers, p squared over lambda squared, p to the fourth over lambda to the fourth, and we want to keep those things separate. If we do a loop with a momentum cutoff, stuff that was originally order m squared over lambda squared, because m squared over lambda squared is then compensated by a lambda from the cutoff, it looks like this is now the same size as something that originally wasn't that, right? So this guy is order 1, this guy is order m squared over lambda squared, smaller, but if I do a bad regulator, it looks like this diagram is just as important as this diagram. And that ruins our power counting. We no longer have this separation of, I can say I'm only working at a given order in power counting if they all mix up. Dim reg doesn't let that happen, right? And we said that here now we've done that same integral. How does the side to the fourth contribute to the field strength renormalization? Well, now it's suppressed by a power counting. This is no longer the same size as the just photon loop, which was order 1, which is what we had at tree level. At tree level, we had this vertex is small compared to this vertex. Now we have at loop level, loops with this vertex are small compared to loops with this vertex. So I can maintain this separation. Here's a small set of diagrams, order 1, small set, order p over lambda squared, small set, p over lambda to the fourth, and they don't mix up. Okay, wonderful. Please, questions like that are super important. How far we go is not. All right. Also, it seems like the RG equations are correct even for large epsilon. You haven't made these small epsilon approximation. Whoa. Yeah, absolutely. You're right. I agree with you. We're going to make the small epsilon expansion eventually. We haven't done that yet. The last thing I need, unless we got more questions, I'm really after this guy, ZC, and it's tangled up in this mess here. So I got this guy, Z psi, by itself. Now I need to figure out what this counter term is so I can peel out ZC, normal problem that we always have. So I want to get at this guy, mu to the 2 epsilon. Well, that's going to come from loops involving corrections to that vertex. So we're going to have terms like, and here's our 1, 2, 3, 4. And the reason I'm doing it this way, this is great notation that I'm stealing blatantly from Skiba. This is saying that we have we know that because of our stupid toy example, there's two possible fermion contractions. So U bar 3U1, or there's U bar 3U2. This way of doing this is just saying I'm specifying this contraction. For those of you who are curious about that sort of thing. Plus, et cetera, et cetera, et cetera. So there, no, I shouldn't do et cetera, et cetera, et cetera. This is it. It's this plus, I'll call flips. Basically means I could do a loop here. I could also do a loop there. But if epsilon is big, you don't get the pole. Let's push on with this. I do not quite understand your question here. Let me think about that. I'm just not prepared to think about D greater away from 4. Let me get back to you. I'm sorry about that. Okay, sorry. By this, I mean this is a diagram that looks U bar 3, U1, U bar 4, U2, and not U bar 3, U2, U bar 4, U1. Both of those are possible contractions. All I'm doing here is just a simple way of saying how we can steer the fermion number, right? Right? There are, of course, loops involving opposite contraction things. They're just going to go along completely for the ride. Does that clarify things a little bit? Not physical at all. They're just a notation thing. Let's call this A, B, and C. Go ahead and A, you would have to do some loops. For the sake of time, I'm not going to do any of that. I'm just going to write out the result. Again, all I have to care about, 0 all masses, 0 external momentum, because I care about that 1 over epsilon piece, because I know that is friends with the mu piece. This is going to give me ICR over 2, 8, 16 pi squared, 1 over epsilon plus finite. Okay. This is part of the problem or part of the program. You would think, good, let's add in B and C. There's a problem with B and C. The problem is that they don't generate the operator that we started with. Right? We care about this operator. If we go ahead and do these loops, we'll find we're getting a number that looks like U bars. Which is essentially the operator sigma mu nu I squared. So when we did a loop, we didn't just renormalize or change the coefficient of the operator we started. We generated a different operator. This is not bad. This is just a thing that happens and it's a fact of life. This is operator mixing. These operators same symmetries, same fields, same dimension. It's not surprising that they can mix. And this is exactly what happens. So we headed our matching C, we'll now call scalar for the coefficient of this operators. Mu equals 1. Well, we knew how it was that was not equal to 0. We just have to have an extra operator. Well, loop corrections also generate higher dimensional operators. Good question. Hold on a second. CT mu equals M. We knew from matching that was true, but nothing says anything about one loop. Sure, the coefficient of what I'll call these tensor operator was 0 when we matched it, but through running, it's generated. Now you could ask, what about the other dimension 6 operators? At high enough loop order, they should be generated, at least the ones that have all the same symmetries here. So maybe the vector current pair of those. Is it going to generate even higher dimensional operators? Dimension 8, 10, no. The whole point of doing these things in DimReg is our power counting is always preserved. This will maybe generate additional dimension 6 terms, but it will never generate extra dimension 8 terms. At least what we've done here with these loops of this vertex here. What will generate loops of dimension 8 terms if I take C and I put two C operators next to each other. So it's not true that no loops will generate it, just new loops of one insertion in C and numbers of photons. That won't. So we've got operator mixing. This is a fact of light that happens in all EFTs. Operators mix up. What does this mean from a practical standpoint? It means I should have put this into my Lagrangian. I should have put it in with tree level coefficient 0, but that still means that I can put in a counter term for it. That also means we have to know, we would have to evaluate loops like here is a vertex of this sigma mu nu structure. We would have to do this loop and of this loop. We would have to do those loops as well. I don't want to do this. This is what happens here is a case of I'm picking a toy example and go, this is cool. Why don't I do this toy example? I wonder why no one's done this toy example before. This is the reason, because then you have to deal with operator mixing. What does this mean if we want to do the full renormalization? Do we want to write down all the dimension 6 operators and do the calculation? I would answer that as yes. You would say I have them all at matching, where at least for our toy theory, only that one is not 0 and all the others are 0. And you would write down the matrix of how they mix up amongst each other. Now that matrix running is always defined, or we're only doing this at one loop order. So I would certainly get how they mix at one loop. If I want to see how they mix at 2 loops, that's a different matrix. 3 loops, etc. Yes. So the answer to your question is yes, but in practical purposes for tree and loop level, one loop level stuff, usually it's the subsets that mix with each other. But that's a very good question. What are we going to do in face of operator mixing? We are going to cheat. We're just going to ignore this. I want you to know that it is there, and I'll write down how you would think about the full results if we had included this. But in terms of actually solving an RGE, I just want to pretend that this guy is the sole result from those loops. So please pardon me, I want you to drive home the message, operators in general can mix, and the answer to this question, if your theory has a good assumption, it can include certain operators. Absolutely, that's absolutely correct. Right, so it's very interesting if you're looking at a theory, which operators can renormalize into each other. And I'll say something about that when we get to the SMEF part. So we're going to ignore for now. We'll put for now here so that people reading these notes don't think I'm a horrible person. So I'm just going to pretend that this is the sole result of our loop calculation. If it was, we could then solve for ZC. It's 1 minus 6e squared, 16 pi squared, 1 over epsilon. Now I have all of the ingredients for my RGE. I have this, and this is what I want. Plug in. That minus 2 epsilon minus 1 over ZC, mu dzc d mu equals 1 over c mu dc d mu. We only do this only working the order e squared. Those are the only diagrams that I've calculated. It makes no sense, or I'm doing things illegally if I try to put in other effects outside of that. So we know this guy's first corrections are at e squared. Therefore, I can approximate this as 1. If I deviate from that, I'm going to more than e squared. So this we're going to eventually just set to 0 because we know we're going to send epsilon to 0 at the end of our calculation. I have mu dzc d mu there's no mu dependence explicitly in Z. Right? Z depends on E, and E is the running electromagnetic coupling. So Z depends on mu only through how it depends on E. So this is dZ dE mu dE d mu, which we can do some derivatives here. Minus 12e, 16 pi squared, 1 over epsilon. And now we need mu dE d mu. But I already wrote that down. Mu dE d mu, working to consistent order in E, is just minus epsilon E. And we see our epsilons cancel out, and we get, there's a minus in all of this, minus 12 e squared, 16 pi squared. The fact that C was the coefficient of a non-normalizable operator never played a role. By working with dim reg, we never generated operators of different dimension, and we never had operators of different dimension, different power counting, feeding in. Therefore, we maintain this separation that we've wanted to maintain. This guy is the anomalous dimension. So, thank you for that patience. We can now enjoy, in the last few minutes, the results. So we have mu over C, dC d mu, minus 12e squared, 16 pi squared. So we have C as a function of mu is in terms of E, and E is also a function of mu. That's just how the running coupling works in electromagnetism, but we know that. So we can just solve. The way you usually solve this is I write this as 1 over C dC d alpha. Of course, alpha is just E squared over 4 pi. Mu d alpha d mu. Hey, we know that. That's our beta function for QED, equals minus 12 alpha over 4 pi. So now it's a differential equation in alpha. End of the day, just solving that differential equation, you will get C at some low scale m is C at this high scale, capital M, which we know is capital K squared or M squared, alpha of M, alpha of capital M, to some power. Okay, why do we care? Well, in order to see why we care, we need to expand this guy out, or at least in order for me to see why we care, let's expand this out. In order to get alpha M and alpha M, this is just, sorry about that. In order to get this ratio, that's just solving the beta function of QED, which we've done. We do this, Schwarz does this, Peskin does this, we know this. So I know what that ratio is. So if I put that in there, this is equal to, right, this coefficient here times see, the log is now in the denominator, right? If I were to expand this, we would have 1 minus 9/2 times 2 alpha m pi log m over m plus dot, 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 dot. What we have done, we have resummed this series in logs. Log plus alpha squared log squared plus alpha cubed log cubed. We've resummed this whole series into that. So by solving, treating this EFT as a theory in its own right, starting with this condition starting at M, solving its RGE down to little m, we have resummed. If you like plugging in numbers, you can plug in big numbers for this guy, and our perturbation theory is better behaved. We've resummed all of those effects, right? When we started this, way back here, we had sort of like loop soup, right? We had combinations of orders K, that Yukawa coupling, badly named, and E. What we've been able to do in the EFT is zero in on a specific order in the power counting and resum the perturbation in a different counting. So we've kept to order p squared over m squared and resummed all the electromagnetic loop effects. We could do that at p over m to the fourth, p over m to the sixth. This way that we can sort of pick and separate our orders of perturbation, keep one fixed order, resum to all orders in another, is really super useful because we can, resum the things that are biggest while maintaining a perturbation theory and things that are smallest. This set of tools is now totally available to us using EFT framework. The fact, and I don't need to repeat it, that being non-renormalizable didn't matter because we managed to separate these power counts. The thing I will end with is just, what if we had done this problem right? What if we had included the operator mixing? Well, then I would have had a 1 over CS, we'll call it. That's the equivalent of that scalar coefficient. And 1 over CT, mu dCt. I would have had 2, and they could be entangled, meaning they could be functions of not only E, right? When we did things, we only had this, and it was only a function of E. Once I conclude them sort of coupled together, they could depend on E, CS, or CT. Right? There's no reason that my Z would have to be so simple. Right? So in the end, I will have to write this as a matrix equation. Equals that CS CT. Right, and we've worked out this entry. How does CS run there? In general, this would have 4 entries. What do we have to do when we have a system to a 2x2 system in a differential equation? Well, I've got to find the eigenvectors, find the combinations that scale simply, solve them for the, or figure out how the eigenvectors scale. And the eigenvectors here are some linear combination of those couplings. Scale them appropriately, and then rewrite the eigenvectors into CS and CT. So it's a more complicated problem, but it's just more linear algebra on top of what we've done. The physics is the same, meaning, sure, we may have more than one operator that we have to deal with, but we're not mixing dimensions. And we can still do this resumming things. So we have gotten rid of this potential headache of having large ratios of scales invalidating or making perturbation theory difficult by having this resumming things. So we're essentially out of time. I want to try and address whatever calculator confusion people have got going on here. And if I can't, I may just have to give you an answer for next time if I don't quite understand. Otherwise, feel free to shoot me questions here. So we've got a question here that for other D, the pole structure will change. If one's big, you don't get the pole. Don't get the pole. Poles are in, I don't quite understand what you're imagining is happening is bad, but that's probably just a failure of chatting, typing questions. So.
When I saw that, what I was thinking of is you could go backwards a step in dim-reg and like Peskin and Schroeder, and you look at where the 1 over epsilon poles are coming from. It's some expansion of the capital gamma function of
that's right.
Like D minus epsilon near integer values where gamma is divergent. And then, yeah, so maybe this is just the issue.
Oh, that's true. Sure. Sorry, that's right. So as Heather's saying, right, if you are doing that, so you're seeing those poles there because I'm expanding near 4 dimensions. That's right. If you were expanding near D equals 2, you would have different things there. So that's absolutely true.
Yeah. I mean, you still get poles, right? Any place near any integer dimension, but if epsilon is like 0.5 or something like that, then you're kind of like, yeah.
If I recall, sure, the fact that poles canceled in those dimensions, this is more specific to different loops, right? Certain loops, right? This will come up in the next lecture when we talk about quote unquote quadratically divergent things. Yeah. So that issue, hold on to that question. I hope to address that or at least get back to some of that next time. There's also a question, if we make spin 1 to be massive in the broken Higgs phase, there will be 2 characteristic scales, MA and M. Well, you have to tell me where MA prime is, right? Is it one of my light degrees of freedom? or is it a heavy degree of freedom? If it's a heavy degree of freedom, what does the EFT procedure say? It says, like then we would integrate it out, and I would have only 4 fermion operators again. I would have ones generated from scalars, but I would also have ones generated from vector exchange as well. And if it's a light, sure, it would be a light thing as well. This M that I'm sort of carrying around here, that just is sort of representing masses of all of the characteristic light fields that we're talking about in this particular calculation. So yeah, everything that we would say certainly is going to hold. You would have a different starting EFT because I would have integrated out a scalar and a vector, but everything else would be just as similar. It'd be more complicated, but it would be similar.
Maybe while people are thinking about and typing questions, I wanted to say, like, the first place I learned about this operator mixing and running and all of this stuff was in the context of B physics.
Yes.
This is like, when you're doing B physics, you make an EFT where you integrate out the W and the top quark, and then, you know, all of those like bottom
C9,
quark decays.
C9 prime, C10.
Exactly, like those
exactly.
are all C9, C10, all that stuff that we were hearing about last week. Those are basically coefficients of dimension 6 operators of like 4 quark things. Or no, sorry, 2 quark and like a lepton and something.
And if you go on even farther back, this is the story of the delta equals F rule.
Yeah, that's right. It doesn't quite explain that, right? But yeah, explain some of it.
It can explain some of it, but the story is that, you know, your low energy coupling constants can be bigger or smaller than you thought they were.
Yes.
You know, depending on how the guys run as they come down from the high scale.
Yeah, this is super crucial physics in tons and tons of contexts. So yeah, absolutely. Yeah. Right. I didn't even mention by zoo of EFTs that, yeah, when Heather is talking, well, I guess it's a Fermi theory. You integrate out Higgs W top, you've got your theory of light quarks and leptons. And yeah, that's an EFT, which will renormalize, which will mix up all those nasty operators. Absolutely.
And like beta S gamma is a classic example of like a nightmare process where there's operator mixing and all kinds of stuff.
Absolutely.
Fortunately, somebody's already done it.
This is true.
Exactly. So if you want to see an example, go look up some review on beta S gamma, and you'll see all of this stuff.
In the SMEFT. So we will. Well, yeah, I don't know. In SMEFT, there's a huge number of operators. So I will, you know, illustrate that has been done. But yeah, absolutely. In how to evaluate the divergence of loops that contain no mass scale. Ah, this is a great thing about DIMREG. Whoops. If I have, let's say, k to the 4th, there is no mass scale around. Right? There's no mass scale in here. Right? This guy, 0. Yep, exactly. Dimension in DIMREG, dimension. Yes. Is there a time when people choose 4 + 2 epsilon? Absolutely. If people are worried about infrared bad behavior. So for example, if you're doing something like, let's say, E + E- to QQ bar with a gluon, right? When you're doing the 3-body part of that, the 3-body phase space, there are certainly infrared divergences where, say, the gluon and the quark are collinear or the gluon is super soft. In order to isolate those pieces, people use DIMREG in 4 + 2 epsilon dimensions. Absolutely. Epsilon is just a number. You can make it go whichever way you want here. Integral of 1 over k squared is 0 by DIMREG except in d = 2. This is right. Often people write exactly that. It looks like 1 over epsilon UV minus n over epsilon IR. That's right. Would the renormalization of vacuum energy be relevant? Well, vacuum energy is not something that we observe, right? It's something that people worry about with gravity, but yeah, this is a good question. I don't actually know the answer to how we think about that in DIMREG. Yeah, you know, in cutoff, you'd say, oh, that's lambda to the 4th. Terrible, terrible, terrible. Yeah, I think in DIMREG, you would say, this actually relates. We're not going to talk about quartic divergences like the vacuum energy, but we will talk about quadratic divergences for something like a scalar mass next time. And we'll talk about what DIMREG has to say there. So while I don't know an answer, I would just say DIMREG's telling you it's 0, but I have thought about this, not at all. We'll see exactly the role on how quadratic divergences show up when naively all you've got in DIMREG is this 1 over epsilon business.
The 1 over k squared example. Okay. Yeah.
An integral of 1 over k squared, for example, in calculating correction of Yang-Mills propagator from the 4-point interaction. It's important in D equals 2 Yang meters when using DIMREG.
Yeah, I think this is true.
I believe that that's true. Yeah.
Poles in the gamma function both at
That's right. Certain types of diagrams look like they have poles in multiple places. Yeah. I've been sloppy here and haven't been exactly, you know, I told you where those poles are coming from. Yes, thanks. Yeah, Heather's exactly right that they're coming from that. Can we go into the counter term of VEV? Well, what VEV? I've never thought about this. This still striking me as funny because I don't know how it gets around that argument. What scale is it proportional to? I absolutely buy it could, right? When we were doing things like motivating why DIMREG preserved our power counting, right? We had things like, you know, 1 over k squared minus m squared. So there, you know, there's another scale in the problem. And if a dimensional analysis tells me it's got to be proportional scale, I've got it. For your example, I don't know what scale would be out there, but
no, I think it just, you just get the log mu squared and then you absorb it all into the counter term.
You don't get a 1 over epsilon?
Oh, you get a 1 over epsilon, you get that log of 4 pi, you get the Euler-Mascheroni constant, and you get the log of mu squared, and then you just absorb the whole shebang into the counter term.
And DIMREG basically throws away the power divergences and keeps the logarithms.
Yeah.
You could have done your entire calculation at one loop with a hard momentum cutoff. You just would have had to push a little bit higher in the thing. You know, there'd be a lambda squared term, which you would absorb into a counter term.
Sure. It's just harder, and at least in the intermediate steps, looks like it juggles the power counting. Yes.
It's annoying, but what the hell?
That's right. Right. I mean, we also like DIMREG because it preserves gauge invariance. So, yeah.
Yeah, that's kind of important depending on what you're trying to calculate.
On one of my pieces of paper is to mention, but yes, there's other reasons to like DIMREG too. In addition to that, it preserves this. But yeah, none of the arguments that I'm using here, you know, it's probably easier. I find them easier to see in DIMREG, but they don't rely on it. You're exactly right. It's harder to do it that way, but we get there in the end.
And there are, like, you can use symmetry violating regulators as long as you like fix things afterwards. Like there's techniques for doing that as well. Right.
Symmetry violating regular. Yeah, I think so. But I have no hands-on experience with this.
Yeah, it's a pain in the butt, so people don't usually do it. But I think sometimes people do it in supersymmetric theories because DIMREG breaks SUSY, and
DIMREG's kind of
there's another version that people use instead.
Right.
We have to deal with that when we do lattice perturbation.
When you guys, you really have to deal with that.
It's an incredible pain in the backside. And you don't want to do this if you can possibly. You don't want to go there. Just don't go there unless you're forced.
Yeah. Okay, we should probably give people a break. Coming up at 3:45 is the discussion session this afternoon with Shifang Su and Laura Reina. And yeah, so there's an algorithm. Basically, if the sun is shining on you right now, you should go into room.
Yes, Ethan's algorithm is very complicated.
Ethan's algorithm, yeah.
Well, this is the next to last discussion session, right?
That's true.
To make it interesting, if you can see the sun out your window, you're facing west, so go to room mu.
Right. And if if you saw the sun out your window this morning, assuming it wasn't cloudy, then go to the other room, room E, I guess. I'm trying to find where it's posted.
Heather, think
Yes.
about what you just said.
What did I just say?
So the sun's in the west now, but in the morning the sun was in the east.
Exactly. So if you see the sun out your window in the afternoon, go to room U. If you see the sun out your window in the morning, go to room E.
In east-facing window, you'd see the sun in the morning.
Exactly.
Afternoon.
Yeah.
That's
for
my
east.
Yeah. It's a model question.
Okay. Yeah. And if that's just too confusing, flip a coin and go to the room it tells you.
Whatever window's closest to you right now.
Yeah. Okay. All right. Talk to everybody later.
Yes. Thanks, everybody.